Welcome to the Introduction to Real Analysis. We will delve into rigorous calculus, epsilon-delta proofs, and the foundations of mathematical analysis. Get ready to build a solid mathematical foundation for calculus. Real analysis is the rigorous study of functions, sequences, and series of real numbers. It's about making calculus concepts mathematically precise, providing a deeper and more accurate understanding of the fundamental principles. We will transition from calculus intuition to real analysis rigor. In calculus, you might think of a function approaching a value or infinitely small changes, and rely on geometric understanding. Real analysis, however, uses precise epsilon-delta definitions, rigorous proofs, and logical foundations to formalize these ideas. Let's look at the epsilon-delta definition of a limit. The limit of f of x as x approaches c is L, which is written as limit as x approaches c of f of x equals L. This holds true if for every epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. Let's break down the epsilon-delta definition. Epsilon, denoted by the symbol epsilon, represents how close f of x must be to L, essentially the tolerance for the output. Delta, denoted by the symbol delta, represents how close x must be to c, which is the tolerance for the input. Here's the strategy for an epsilon-delta proof. First, given epsilon greater than 0, find delta greater than 0. Second, show that the absolute value of x minus c being less than delta implies that the absolute value of f of x minus L is less than epsilon. Let's look at a simple example. We need to prove that the limit as x approaches 3 of 2x plus 1 equals 7. Given epsilon greater than 0, we need to find delta greater than 0 such that the absolute value of x minus 3 is less than delta, which implies that the absolute value of 2x plus 1 minus 7 is less than epsilon. We can simplify this to the absolute value of x minus 3 is less than delta, which implies that the absolute value of 2x minus 6 is less than epsilon, which further simplifies to the absolute value of x minus 3 is less than delta, which implies 2 times the absolute value of x minus 3 is less than epsilon. Continuing with our example, we need 2 times the absolute value of x minus 3 to be less than epsilon. To ensure this, we choose delta to be equal to epsilon divided by 2. Then, if the absolute value of x minus 3 is less than delta, which equals epsilon divided by 2, this implies that the absolute value of 2x plus 1 minus 7, which equals 2 times the absolute value of x minus 3, is less than epsilon. This completes the proof. Let's explore some key concepts in real analysis. Continuity refers to functions without jumps, and it has a precise definition using limits, which forms the foundation for derivatives. Sequences and series involve convergence and divergence, giving us a rigorous understanding of infinity and serving as the basis for integration theory. Why should you study real analysis? It develops mathematical maturity and rigorous thinking. It also provides the foundation for advanced mathematics and its applications. Ultimately, it helps you master the language of precision in mathematics. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.